Okay, let's add up a little bit more complexity to what we have learned already. Okay, and we are not going to add up complexity by considering a five or a six input truth table, though you can read up about it in the textbook. What we are going to do is, when you write truth tables, sometimes there are some conditions in which you don't care what the output is. It doesn't matter whether it's 0 or 1 for a particular condition. It doesn't matter to you. Okay, and so these kinds of conditions are called don't care conditions. So for example, I could say, for example, let me fill up this k map, and then we can talk about something. So for example, I want a 1 for this combination. I want a 0 here. I want a 1 here. I want a 1 here. 1 0 0 1 0 0 1. Okay. But I don't care what the values are at these squares, let's say. Okay. So the way you represent these conditions are called don't care conditions, right? You don't care what the output is when the inputs are in these uh, when you have these combinations of the inputs. So what you can do is you can put an x for those don't care conditions. And when you're minimizing, when you're using your k map and trying to minimize the boolean expression, what you can do is, depending on your needs, you can use this x's as ones, or you can forget them and take them to be zeros. Okay, so let me give you an example. So for example, what I could do is I could say, I want to cover all the ones, right? Now, can I group this particular one with any other one on the table? I can't. So what I do is what I can do is I can take this x to be 1, this to be 1, this to be 1, and then I can group all these x's into one group, right? So I can make a group like this. And then what I'll get is I'll get a much more simplified equation than if I had written the minterm for only this one. Okay. Similarly, what I can do is I could group these four into one group, and that would kind of give me another group, right? uh, and then what I can do is I have these two ones, and it seems as if you can't combine them with any other ones till you remember that this column is actually adjacent to this column and this row is adjacent to this row, right? So what I can do is I can write it like this. So that's one group again, which consists of these four ones, this, and this. And so now what we have done is we have three terms in our expression, right, in our output. So let's write those terms. So you'll have f, let me write it in blue. So you have f equal to what? So if you look at this outside grouping, you can see that between these two rows, D remains constant while C is changing, so C disappears. And between these two, A is changing, so A disappears. So you have B bar and you have D bar. So your term is going to be B bar D bar plus, let's take a look at this group. If you take a look at this group, CD disappears because all combinations of CD are appearing here, and you only have A bar B. So let's write that, A bar B. And lastly, we have plus, we are looking at this group. So this group, all combinations of A and B are coming here. So A and B will disappear, and you have only C bar D bar. So you can write C bar D bar. And that kind of gives you the minimum um, possible Boolean expression for this particular truth table or K-map, right? And you can notice that what we have done, we have left these x's alone because we just assumed that these x's are zero. So basically, what I'm saying is that if there are don't care conditions, then you can intelligently select those don't cares to be one or zeros so that you get a minimized expression.